Now, interesting example is, what can I say about this again? Of course, this was convex. Definitely, this is convex set. Do you agree? Take any 2 points here and join them, you still get a point, right? So, okay. So now, do you think this is a cone? How do you prove that? Very easy. You take a point in the S plus plus n, that means a matrix. You scale it by a non-negative number. Of course, it was symmetric. Again, it remains symmetric. It was positive definite. It will remain as positive definite, right? Well, small catch here. If I use alpha greater than or equal to 0, if I put alpha equal to 0, it will not be there in the set, right? So this point is not there. So what do? I'll just remove this plus plus to 1 plus. That means it's a set of all symmetric, positive, semi-definite cone. It's a cone, right? Is that fine? So now, why do you need this? Well, thinking, so I can think of Sn plus as cone, right? So I can imagine now. I have some way of visualization. Otherwise, I don't know how to visualize S plus n, right? It's weird set. Now, why is it useful? There are certain problems. For example, I can say, okay, so those who know some very complicated things like this, okay. Maximize overall sigma, sorry, such that sigma, I want this to be symmetric and I want it to be positive definite. Why? It's some power allocation. So power cannot be negative, right? So I can say that this belongs to, I can always do that. Well, this is maximization of some log det function, which is complicated. We will see such functions later, but subjected to a conic constraint, right? So I can think of each sigma belonging to a cone, right? Well, there is one more constraint, which is I cannot use any cone. I can take the matrix to infinity and use infinite power. That doesn't make sense. So I want it to be less than or equal to some constant, let's say p. Okay, this is Frobenius now. Okay, don't worry about this constraint. This will say that it should also belong to a circle. So what? How does this? See now, how do I visualize this? The first one says it belongs to a cone, right? This is how it looks like. Well, not exactly this, but this is how I can visualize. Frobenius norms less than or equal to p, or Frobenius norm squared less than or equal to p. What does that mean? That forms a ball, right? Circle. So it's like this. It is all the points here, right? This is how I can visualize. This is my constraint set. Right? At least I have the ability to view things now geometrically, right? Otherwise, this constraint set. I mean, have you ever imagined? I can think of it as actual ice cream, right? Well, not really. I mean, yeah, ice cream filled, cone filled with ice cream, right? So this is how it looks like, right? I mean, nobody could have imagined that. I can imagine this constraint set this way, right? Well, it has some use, not that you can just visualize. You can also use that visualization to come up with better algorithms and so on. Okay. Any questions so far? Right. So we have studied cone and we have studied convex sets. Right. So in the next class, we will see a few more examples, and we will see how to convert a non-convex to convex set. So for example, if I have this set, right, how do you convert this into convex set? Why do you need to do that? Well, it's difficult to deal with non-convex, right? I have to, convex is always nice. How do you do that? Huh? What do you do? All that I have to do, again, geometry, right? So I have to just do this, right? Join this line and fill this hole. Now this hole I have filled, and of course this was there before. Everything put together is a convex set. This is called convex hull. Okay, so you just fill the gaps and make it convex. That operation is called convex hull, right? Many a times, the reason why we do this is a very good approximation for convex sets. So hopefully, we can solve this problem, then I can solve the original problem pretty accurately. Okay. So any questions? So I'll stop here. We have 2 more minutes. Any questions?